Oh, hi. I'm Joseph. Today we are going to talk about the thermal expansion. This is the first topic in the thermodynamics, and I think if you didn't learn physics before, we will meet something new in this topic. So I will spend some time talking about the basic idea of the thermophysics and why we need this, and then I will talk about the homework solutions in the chapter 17. Yeah. So first of all, I'm going to talk about the first question, and you can see I have a description here. This is homework 17.6, and we are going to convert the following Kelvin temperature to Celsius and Fahrenheit scales. And there are three parts. So the first part is that we are going to convert the 400K to the degree in Celsius and Fahrenheit. And the second part is 95, and the third part is this number. Okay, so we may have some question that what's the difference of the three scales? The Kelvin scale, Celsius scale, and the Fahrenheit scale. If we just talk about the history, how people define the temperature. The temperature is a physical property to describe how heat the environment is. So there are many ways to define the temperature, and we use the thermal expansion to define the temperature. So the first thermometer is use the water to mate, and because the water has different volume at different temperature, so we can use the volume of the water to quantify the temperature. So in the 18th century, there is a German physicist, and his name is Fahrenheit, and he just defined the temperature in this way, and he said the temperature of the freezing point is 30 degrees, and the temperature of the human's body is 90 degrees. And this is roughly, this is not accurate, we know, but at that time, this is how he defined the temperature. And he just divided the temperature between 30 to 90 linearly, and he got different temperature scale. So this definition is called the Fahrenheit scales. And another physicist in Sweden, and his name is Celsius, and he used another scale, and he defined the temperature in this way. He said the freezing point for the water is 0, and the boiling point is 100, and the people can divide the temperature from 0 to 100 linearly. Then we have another definition of the temperature. So both these two definitions, just because of the history, so we have two different temperature definition, but these two temperature could be convert each other. So here is the definition. So if we know the temperature in Celsius, and we are going to calculate the temperature in Fahrenheit scale, then we use this formula. So this is a linear relation. And some people are familiar with the temperature in Celsius, but people in American likes to use the Fahrenheit. So this is just depends on the preference. But these two temperatures are not the physical international standard definition. So we use a different technique to reach the different temperature. So here is a chart. This table shows different temperature in different case. So from the high temperature to the low temperature, we have that the temperature in the Big Bang here is very high. So after Big Bang, the universe is very hot, and this number is very high. And if we just look at the degree in Celsius, we have the order 10 to the 32. So that's very high, and I have no idea how does this temperature feel like. Okay, and if you just study the nuclear weapon, when the nuclear weapon explodes, then this temperature is millions degrees in Celsius. And another temperature is the sun's core. The temperature in the sun's core is 16 million, also very high. And if we just go to the sun surface, it just decrease a lot. And also the temperature for the lamp is 2200, and the melting point for the steel, the iron, is 1500 degrees in Celsius. And for the water, the boiling point is 100, and the freezing point is 0. So these two temperatures are very familiar for us. And if we just keep decreasing the temperature, and we know the microwave background in the universe is this guy, and also the dry ice has a temperature in negative 78, and also in Celsius. And if we want to get the lower temperature, we have the liquid nitrogen. The liquid nitrogen is this low. So the next question is that, can we go lower? So actually the thermal physics is just confirmed that there is an absolute 0 point. That means we cannot decrease the temperature below this number, negative 273 degrees Celsius. So this is very interesting because there's no high limit for the temperature, but there is a low limit. So we just call this low limit as absolute 0. So when people discover this number in theory, people just define the temperature in another way. That is, we just set this number at 0 degree, and then every temperature just plus the intersect. So we define this as 0, that all the degree in Celsius plus 273, then we get another number. This number is called the temperature in Kelvin. So the Kelvin and the Celsius have the very linear translation. And if you know the degree in Celsius, then you just plus 273, then you get the degree in Kelvin. So if we know the degree in Celsius, then we plus this number, and we got the degree in Kelvin, and the unit of the temperature is Kelvin. So this is an important unit, and this is international standard. And if we don't mention other units, we just have a default unit, that's a Kelvin. So if you do any physical questions or the problems and homework later, we encourage you to convert all the temperature in Kelvin, not Celsius or Fahrenheit. Okay, this is an introduction of the 3 units. And after you have these 2 relations, then it's very easy to convert this number. Okay, the 3 numbers just put inside in these 2 equations, then we can get the degree in Celsius and Fahrenheit. So let's watch the the calculation. So here, the first number we're going to calculate is 400 Kelvin. The 400 Kelvin, in the first equation, then we get the degree in Celsius. After we know the degree in Celsius, we plug into the second equation, then we have the degree in Fahrenheit. So this is the calculation and solution. I think this is not difficult, so I don't read it. So you just use these two equations, and then after you get the result, you compare with my solution, then to see if you got the right result. Okay, so I think the very important is the unit. I think some of the students might neglect the unit. We have to be very careful. When we talk about the Celsius, the unit should be a degree. This is a circle, up circle. Then we use the C, capital C, to represent the unit. And for the Fahrenheit, that's a small circle on the top, then capital F. Okay, then for the degree in Kelvin, then we don't have a circle, we just use K, the capital K. And this K is the letter we want to give credit to the thermal physicist Kelvin, to recall his contribution to the second thermal laws. And I think this guy is very famous in the thermodynamics. And if you just read some history about this guy, you will get he's very interesting. So this is the first question. Use the formula to convert the unit. Okay, so let me move to the next question. The next question talk about the thermal expansion. So this is a very interesting question, and we are going to talk about if the temperature change and how does the object change. The length and the volume of any object will change if the environment temperature change. So we call this thermal expansion. If the temperature goes high, then they expand, and if the temperature goes low, they just shrink. But this is not the absolute physical law. Sometimes you will get an inverse expansion. For example, if you have water and the water go to the temperature below 10 degrees Celsius, then you will find if you decrease the temperature, then the water just expand, and if you increase the temperature, then the water just shrink. So this is very interesting. So I just say the thermal expansion is not for all the object. And here we have a question talking about the steel. So there is a very tall building in Taiwan, and the name is Taipei 101. So I show you a picture here, and you have the reference. These buildings are very short compared with Taipei 101. Okay, this is a very famous building, and if you have any chance to travel to Taiwan, it's very good to just visit this building. And we know the height of this building is 1671 feet, and assume this height was measured on the cool spring, and the temperature is 15 degrees Celsius. And after in the summer, when the temperature goes high and we measure the height again, we find that this building is becoming taller in this number, and then its original height in the spring. So this is very interesting because the building just become taller, and the change is very tiny, and 0.47 foot, and this is not very large, and I think most people cannot feel that. So if we find this difference and we know the different temperature, then the question is, what's the temperature of this building in the summer? So if we just know the initial temperature and the initial length of this building, and we know the change of the height in the hot temperature, then how can we determine the temperature in summer? So here is idea I show you here. So at the beginning, the length is L none, and the original temperature is T none. And if we just increase the temperature, and this rod just expand with delta L change, and just increase delta L, and the temperature increase by delta T. And we find that if we do the ratio of the change length over the change temperature, then we got a number. This number is a constant. So we call this number as coefficient of the linear expansion. So that means if we have a specific material, and this material will have a certain number, and this certain number describe the ability to expand when we have a change temperature. So this number is very important, and you don't need to remember this number. We will provide this number to you when in the exam, but the idea is simple. That means if we change the temperature and the length change, then this ratio is a constant. But I have to say that this number, the coefficient, is not constant always. So if you read some books about the temperature in a very low or in a very high, I think this number, this coefficient, should be a function of temperature. But I think in the room temperature from 0 to 100 degrees in Celsius, this ambient temperature for the normal life on the Earth, this number change a little bit. So we can just treat this number as a constant. But if this temperature goes very high to the 1000 degree or the minus 200 degree, very hot or very cool, this number changes a lot. So we cannot use a constant number. But in this problem, we just assume this is a constant number. And we know in the spring and in the summer, this temperature doesn't change a lot. So a lot here means it's compared with the temperature change on the sun or on the other star. But in the Earth, this temperature change is very even. Okay, so we just treat this number as a constant. Then, if this is a constant, we can just go to the Google or to go to the Wikipedia and to find this number. And here I got for the steel, and the steel we have the coefficient for the thermal expansion is this number. So you can find that per degree in Celsius, the ratio change is 10 to the negative 5. So this is very small. So for the steel, you cannot feel a very large change. So let's go back to this question. And we know the coefficient for the thermal expansion is this number, and we know the change of the height, and that's 0.471 feet. And we know the initial height for this building is 1671 feet. So we can going to solve the change of the temperature. So the change of the temperature here is 23.5 degrees in Celsius. And this temperature just reflect the temperature change from the spring to the summer in Taipei. And see, that makes sense. Okay, so if you are not familiar with the temperature in Celsius, you can convert this number in Fahrenheit. And I think 23 degrees in Celsius could reflect the temperature change from the spring to the summer. And I think if you know this the temperature in spring, the 15 degrees Celsius, then your process number is around 40 degrees. So 40 degrees in Celsius is more than 100 degrees in Fahrenheit. So in summer, Taipei is very hot. So if I have a chance to travel to Taipei, I prefer to travel in spring, not in summer. Okay. So this is a question talking about the thermal expansion. And this is the linear thermal expansion, because here we use the length, the height. This is a one-dimension expansion. And if you know the change of the length and the coefficient of the thermal expansion, then you could go to solve the temperature change. Okay, and the next problem is similar, but the expansion is not for the linear expansion, it's a volume expansion. So here we have a glass flask, and this flask has a volume, and this is 1000 centimeter cube at 0 degree, and is completely full of the mercury at this temperature. So the volume are the same. And when the flask and the mercury was warmed to the 55 degrees Celsius, we find that there is some mercury overflows, and the volume of the overflowed mercury is 8.95 centimeter cube. And we know the coefficient of the volume expansion for the mercury is this number, and the coefficient of the volume expansion for the let me see. Oh no, this is not mercury. I think this is something wrong. So let me change it. So I think this is not the. I think we have too many description here, so I just erase it. Okay, so if we know the volume expansion is this guy, then we are going to calculate the coefficient of the volume expansion for the glass. Okay, so let me just clarify what we know so far. We know the initial volume for the flask, initial value of the mercury, both are the same, and we know how much change of the temperature, so 55 degree, and we know some of the mercury overflows, leaked on the table. So we have this guy. So this guy actually is volume change difference for the flask and the mercury. And because when we increase the temperature, both the flask and the mercury expand, but they don't expand the same. So there is a volume change after the expansion. Okay, so let's go back to the formula. And just now we talk about the linear expansion, and we use the length ratio to quantify the coefficient. Now we have another coefficient we call the volume expansion coefficient. And the difference here is that we use the difference of the volume, not the length. So, and we differentiate these two by using alpha and beta as different letter to just distinguish with these two. So here, let's go to calculate the volume change for the mercury and the flask. Okay, so if we know the coefficient of the mercury, then we can go to calculate the volume change for the mercury. So the volume change for the mercury could be solved by multiply the change of the temperature and the change of and also the initial volume. So we have this formula. this formula just get from here. Okay, and we know the initial volume, the change of temperature, and the coefficient here, so we can go to solve the change of volume for the mercury. So we have this guy. This is a change of the mercury, the volume change for the mercury. And we know that 8.95 centimeter cube of the mercury overflows. So that means the difference is 8.95, and we just minus this number, then we got the volume change for the glass flask. So we get this number, and we just use the change of the mercury value minus the volume that overflowed, then we got the volume change for the glass. Okay, so when we have this number, we going to use this formula again, and we know the change of the volume of glass flask over the initial volume of the glass. That's 1000, and the difference of the temperature is 55. So we can go to solve the coefficient for the glass. So I think this formula is not difficult to understand. If you just write down this formula and figure out how many parameters you already know, and in this case, we find that we can solve the change of the volume for the mercury first. So we just solve it. Then let's just figure out what's the volume change for the glass flask. Then we're going to use this formula again, and we got the coefficient for the glass. Okay, so I think if you just know this formula at the first time, and you have to think the physical meaning. And if you understand the physical meaning, then you can go to use this formula very smooth. And I think this is not tricky things for you to understand. Okay, so far we talk about the thermal expansion in linear and in volume. And both these two share the same idea, that is the scale change over the temperature change should be a constant. If the temperature change is very small and we don't go to a very huge temperature change. So I think this alpha and beta, these two coefficient, can tell you some thermal properties for that material. Okay, so let's go to the last question. So this question is engine, the heat engine. The engines can do work, and we use the heat engine to drive the car, to drive the machine. So this is very interesting, and it's also very important for the engineer. So the question said there's a new mechanical engineer for the for this company, and you have been assigned to design a brass piston to slide inside a steel cylinder, and the engine in which those pistons will be used will operate between the 20 degree to the 150 degree, and assume the coefficient of the expansion are constant over this temperature change. So the first question is that if the piston just fits inside the chamber at 20 degree, and will the engine be able to run at a higher temperature? So higher temperature. So why this is a question? So think about that. The piston is made by the glass, and the cylinder is made by steel. They are made by different material, so that means they have different coefficient of the expansion. So if we have the case at the beginning, the piston just fills the cylinder at the 20 degrees C. After we increase the temperature, both the two guys just grow. And we find that the chamber grows less than the piston. Then we find the piston doesn't fit. But if they grow in the opposite way, that means if the piston grows less than the growth of the chamber, then we can use it. So let's just compare the expansion coefficient for these two materials. And if you just go back to the Google and just check the number of these two coefficients, you'll find that for the brass, this number is very high, and 2. And for the steel, this number is a little bit lower than the brass. So we can make this conclusion that we cannot use it because the brass expands more than the steel. So if at the low temperature these two guys just fit, then we increase temperature, the brass will grow faster than the chamber. So this guy is oversized. We can use it. Okay. So this is the first question, and this is a question to help you understand what does the coefficient means. So these two numbers tell you the different thermal properties for these two different material. Okay. The next one is that the next question is if we want to use this piston at a high temperature, what's the size for the piston at a lower temperature? So this is part B. The part B said we know the diameter of the cylinder at the 20 degree, and we want to use this piston at 150 degrees C. And the question is, what should be the minimum diameter of the cylinder at the temperature so the piston will operate at 150 degrees? So that means we know the size of the piston, and we want to know the size of the chamber at 20 degrees C. And to get this number, let's go to the 150 C. And the 150 C will tell you the actual size. So let's go to the 150 C, and we use the formula, the definition of the coefficient, and let's see if this is we can use the information in the 150 to go back to solve the problem in the 20 degrees C. Okay. So we know at 150, these two guys just fit perfectly. So we know the diameter of the cylinder made by the steel should be equal to the diameter of the piston. Okay, and the diameter of the piston at 150 should be solved by the formula and in this guy. So if we know the initial diameter of the brass, and let me erase this guy. Okay, so at 150 degrees C, the diameter of the steel should equal to the diameter of the piston. And let's see, the diameter of the cylinder should be equal to the initial diameter plus the expansion. Okay, and the diameter of the brass should equal to the initial diameter of the piston, also plus the difference. And the difference of the brass could be solved by using this formula. And because we know the change of the diameter should be equal to the coefficient multiplied by the length, original length, and times the change of temperature. So we know the initial diameter of the piston is 25, and we know the coefficients of the broth. We know the temperature change, so we can solve the final coefficient, the final diameter at 150 C. Okay, and we also know the coefficient of the steel. We know the change of the temperature. So in this formula, we only have one unknown parameter. That's the initial diameter of the chamber. So we can solve this equation. So this is the final expression for the initial diameter. And we find that according to the calculation, we can get the initial diameter for the chamber is 25 centimeter. And also we have a small number, small decimal behind. So you can just compare with the piston. This guy should be a little bit larger than the piston. Then we can guarantee this machine can work at high temperature. So this is just an example to show you if you have two different material and you want to use this material and build an engine and to work at a very different temperature range, you have to make sure these two guys fit at different temperature. So this is very important. So actually we cannot have a material that perfectly match at different temperature. So we have to sacrifice some material, and if we know the temperature range, then we have to select a perfect material for both of these two. And we find that not all the material can fit at a long range of the temperature. So this is an example to show you if you have many material and work together and they work for one temperature, but it doesn't work for other temperature. So you have to be careful when you do any design. Okay, so this is what I'm going to talk today. There are 4 problems talking about the thermal expansion. The first problem is how to convert different units, and if you know the 2 equations, you know the relation between the degree in Celsius, Fahrenheit, and the Kelvin, then it's very easy to do the conversion. And the other 3 questions is just to tell you how to use the thermal expansion formula to calculate the change of the volume, the change of the size, and the change of temperature. Okay, so that's all. And by the way, when I made this video, it was Sunday, and it's Easter Day, and I know everybody stuck at home, and this is my first time to teach at home, and I find this very interesting to make video to show everybody here. And for the last past years, I talk with a class, but this time I just talk with a screen. So, but by the way, I know anybody just sacrifice many things and stay at home. So I hope everybody just stay safe. And if you need help, just make a call or send an email. And I hope everybody just enjoying the Easter. Okay, so thank you so much, and I will see you next time.